Okay, so here's where we're at. So we kind of laid the groundwork in terms of kind of like how we do chemistry, okay? How we measure pressure, volume, how kind of atoms act, what units are we going to use? Oh, milliliters, grams. We got the concept of the mole, okay? So now we actually kind of get to start into like the heart and soul of chemistry. So on this packet from this one, so here's this series of questions. You got some big hitters. So Democritus, John Dalton, J.J. Thomson, remember that should be Ernest Rutherford, not Niels Rutherford. And so let me kind of get you through the history of this. So we left off, we talked about Democritus. They were the atomists. They said, hey, if you keep dividing a particle small enough, small enough, small enough, you'll get a point where you can no longer divide it, and it still has properties of being an atom. Okay, cool. Yes?
I need the packet.
So, but unfortunately that view, which made sense, was in contrast to Aristotle. Aristotle said, no, there's 4 elements, air, earth, wind, fire. And so nobody really cared that much about it and that was like about 400 BC, okay? So then you fast forward to about 2,000 years. So this is a very quick timeline of history, okay? And you fast forward to about 2,000 years and you get to the 1600s. And this is what's known as, if you've studied world history, this is like the Renaissance, like the golden age of discovery in Europe. This is where science kind of take over. Galileo dropped the cannonballs, and they both hit at the same time. So then you have to have all this work to support your evidence and everything. And so also in terms of technology, at the time, like to give you some perspective as far as where technology was, the telescope had just kind of become invented. So they didn't have the capacity to refine and measure very, very small quantities, or to do really what we would now consider to be real research. So they kind of had to go off, the hand that they were dealt. And so the first kind of real working, what we call atomic theory, was a guy by the name of John Dalton, and he was an English chemist. And there were certain main parts to his atomic theory. And one was that all atoms of the same element are identical. Don't worry so much about this. I'll explain why this is important. So, what's different now is that, number one, they didn't understand that there were smaller particles that made up an atom. Okay, so John Dalton went back and went retro and pulled up this term atom from the Greeks. And the main point of the story is that he thought the atoms were the smallest building block that you could possibly have. So in this definition, the atom was indivisible, like you could not divide it anymore. So they also thought that, like, if you had an atom of nitrogen, all atoms of nitrogen were identical. All atoms of hydrogen were identical. All atoms of oxygen, whatever they were, okay? They didn't understand this concept of what we call isotopes. Isotopes are atoms of the same element, but they have different numbers of neutrons, okay? So there were a couple of things that we had to revise. This is one of them, is that not all atoms of the same element are identical. And this is going to be part of what we're going to see today with this PhET simulation on how to build an atom, and also like this board game that we've got. So that had to be revised. They also had to revise the idea that atoms are indivisible, okay? So mainly because of the fact they had no concept of protons, electrons, and neutrons, okay? We didn't have the capacity to measure them. Even if you look at, so this is a cool book. So this is a high school physics book. So no, this was not my high school physics book. But this was published in 1902. So this book is 120 years old right now. So if you go back and you look in the index, okay, and if you come back here and if you look in the index and you try and find like the word electron, doesn't exist. The word proton doesn't exist. The word neutron doesn't exist. So 120 years ago, and actually even 100 years ago, we really didn't even know that the subatomic particles existed. So this whole concept of protons, electrons, and neutrons is a relatively new concept if you look at the history of science. So once they figured out that they were neutrons, that led to this idea of isotopes. Now, there are aspects of John Dalton's theory that were right. He said that atoms combine in whole number ratios, okay? So what that means is that you have water, which is H2O. Okay, cool. You're not going to have H3/4O1/8, okay? You're not going to have fractions of an atom combined, because and that played into this whole idea that, oh, atoms are indivisible. So even within that, that's still true, okay? You're not going to have a half of a carbon atom. You're not going to have a half of any atom. Now, can you break them down into those subatomic particles? Yes, but they're still always going to combine in whole number ratios. So that was one of the big things that held true. So if you look at that timing, so this is in like 1700s, that was cool. And so for a long time, that atomic theory held, and it was all good. And so if you look at the kind of the mood of science in the early 1900s, about 100 years ago, the scientific community was actually a little bit depressed. Mainly because if you look at what they had discovered at that point, they figured out what gravity was because of Isaac Newton, his laws of gravitation. That was in the 1600s. Because of that, they could predict like the motions of the planets. They could tell you exactly, like Jupiter's really, really close. They could say, oh, Jupiter's really close. They could predict where Jupiter's going to be 100 years from now. Okay, figured out the moon, figured out the tides, figured out gravity. Electricity was a little sketchy, but they were comfortable with that. And so literally the scientific community was almost depressed because they thought that they had found out, they thought they had discovered everything. And so they literally thought at that time, 100 years ago, like, we've got nothing left to find, okay? We figured out gravity, we've got the atomic theory, we can explain the motions of the planets, you know, we're good. And so literally they thought, you know, nobody really wanted to go into science because they really didn't think there was anything left to discover, okay? Because they thought they had found it all. It's like, oh, okay, we're done. I don't know what's left. So literally their thought was, we need to tweak the constants. Like, okay, maybe we can refine Avogadro's number. Maybe find a better way to measure that. Maybe we can, you know, figure out a better way to measure the mass of the Earth, okay? But literally, they thought they were good. They didn't even know that there were galaxies outside of our own at that point, okay? They literally thought, okay, we have the Milky Way galaxy. They did not know that there were galaxies outside of our own because they didn't have good enough telescopes at that point. So the scientific community is kind of going, oh, what do we do now? So the first kind of big break was a guy by the name of J.J. Thomson. So J.J. Thomson was the first one that discovered the first subatomic particle, and he discovered that was an electron. And so what Thomson was able to do is that he used a cathode ray tube, which I would show you, but mine broke last year, and I can't find any new cathode ray tubes to order. It's kind of depressing, because it was a really cool demo. But it got caught around a cord and tipped over, and it was a glass tube, and it broke. So basically what Thomson did is that he hooked this thing up to a very strong battery, okay? And you have a positive and negative terminal on a battery. But what he noticed that there was a stream of particles that were going through this tube. It was a tube about yay big. It was made out of glass. Okay, so imagine like a really, really like a horizontal glass. Okay, and it narrowed down to each end. And he had terminals, and he would hook those up. And he saw, and these particles would glow. And so what he did is then he also put like another positive and negative plate on the outside of it, created an electric field. And what he found was that these particles did two things. These particles went down towards the positively charged plate, and they got bent away from the negatively charged plate. So he goes, okay, well, this is kind of cool. So these particles went down towards the positive and away from the negative. So he goes, oh, these particles have to be negatively charged. Okay, that's cool. So that was kind of the first big break. It was like, we found negatively charged particles. Okay, what do we do now? So at this point, this turned into a logical situation. Because if Thomson found negatively charged particles, what else did there have to be for the universe to exist? Could the universe exist as we know it with just negatively charged particles? No, why not? What would everything do? Could you build us? Could you build complex structures if everything was negatively charged? Miles, you shake your head no. Why?
Because then they would go away from each other?
Yeah, they'd always just want to repel each other. Oh, you try and put these things together, boom, they're just going to go flying apart. Okay, you could not build stars. Okay, because if you tried to put all these negatively charged particles in one place, they're all just going to repel each other and go flying away. Okay, so it's like, okay, if there's negatively charged particles, guess what? There has to be then positively charged particles. Ah, right. So this created a problem. All right, okay, what do we do now? Because, again, if there were just positively charged particles, we wouldn't be here having this discussion either, because everything would just still repel each other. So, but we obviously knew there were atoms, okay? We did that, remember we did the demo with the balloon and we put the vanilla in it, and we could smell the vanilla on the outside of the balloon. Okay, so there has to be these really, really small particles that we can't see. So if there's negatively charged particles, there has to be positively charged particles. So then it became, well, how do we explain the fact that atoms are stable? And atoms are incredibly stable, okay? As I told you all before, I have been teaching behind this table since 1994, okay? And when I walk in this room in the morning, I have a lot of things to worry about. I don't worry about if this table has changed into a squirrel, okay? Which is what the building that I have up there, okay? I know this table is going to be a table. I don't worry that this thing is going to turn into something else. I know this is going to be a table. So whatever the theory is to explain how the universe exists, whatever it is, it had to be able to explain the fact that atoms are stable, okay? We don't have to worry about them changing into something else. You're not going to walk out and all of a sudden like half the atoms of the iron atoms that make up your car have changed into nitrogen and your car is like evaporated, okay, which would be really weird, okay? You don't have to worry about that. Atoms are incredibly stable. So the other thing that you have to understand is that if you look at this list, J.J. Thomson, Ernest Rutherford, Niels Bohr, Erwin Schrödinger, even though we talk about this in a chemistry class, those bottom four guys were all physicists, okay? The chemists were busy trying to figure out acid-base titrations and how reactions work. So the physics department, this is done in England, okay, mostly, at a university there called Cambridge. So that was kind of the cutting-edge research area of the physics department of the world. So if you were a physicist at the time, this was like in the 1910s, 1920s, okay? Everybody wanted to work with Cambridge because this is where the cutting edge research was being done. So all of these guys weren't chemists, they were physicists. Now, you have to understand the mindset of how physicists take on a topic. So the first idea that they had, and again, this is being done in England. So the first model that they had for an atom was that imagine an atom is like a Lego. A very, very small Lego block. Y'all familiar with that, right? Y'all seen Lego blocks, okay? If you're a parent, you might step on this barefooted in the middle of the night and yell and scream because you stepped on a Lego block. So the first model that they had And this is literally what it's called, was the plum pudding model. You're British, no have plum pudding, okay? So the plum pudding model, the negative and positive charges were evenly distributed within the atom, okay? And it was lovely, and we'll have some tea and crumpets, and life is good, okay? So in the plum pudding model, they wanted to balance the repulsion and attraction because they know they just couldn't have repulsion or the atom wouldn't exist. They just couldn't have attraction or the atom wouldn't exist. So you had to have this balance between attraction and repulsion. So in the plum pudding model, and again, you all have done this. You all did the calculations. Across the thickness of this aluminum foil, there's about 95,000 atoms stacked side by side by side just across the thickness of this aluminum foil. You all did this lab, right? So in this little dimension right there, there's about 95,000 atoms stacked up side by side by side, which means these things are really, 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 really small, okay? So they said, okay, so we're going to have really, 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 really small Legos. And within the Lego, because there's the electrons and protons, we're going to have them evenly distributed. So what that means is that you're going to have some repulsion and you're going to have some attraction, okay? So it's this yin and yang, okay? It's this kind of ancient Chinese philosophy. There's a balance in the universe, right? There's some repulsion, there's attraction, and that explains the stability of it. Cool, life's good, and that worked. Like, okay, right? It's this tiny. It's tiny. We have everything evenly distributed. Hey, we're cool. Okay. But here's the problem. They gave this task to the physics department. So you have to understand the mindset of how physicists view the world. Physicists, at the end of the day, I know this because I teach a lot of physics. We like to kind of smash things. Okay, well that's kind of cool. We like to play with toys. We have helicopters, and I lay on a bed of nails, and we smash concrete blocks on my chest. Okay, so that's kind of their gig. Is that let's smash things together. So here's a classic example. Is that you give a Volkswagen Bug to a physicist, and you say, hey, what's the Volkswagen Bug made of? I don't know. Let's smash it into a wall and see what happens. Okay, cool. So you get the Volkswagen Bug up to about 30 miles an hour and you run it into a concrete wall. And a bumper falls off. It's like, oh, there was a bumper. Okay, that's cool, right? So then they go, if 30 miles an hour is good, 300 miles an hour is going to be better. Okay, so let's get it up to 300 miles per hour and smash it into the wall. Okay, cool. Smash it in there. Wow, there was a door and a mirror and glass. Okay, that was cool. All right. Well, let's get it up to like 3,000 miles an hour, which would be like, about 4 times the speed of sound. Okay, you smashed it into the wall. Oh, there was an engine inside of that. Oh, what's the engine made of? I don't know. So let's take the engine and get up to like, 30,000 miles an hour, and we'll smash the engine into the wall. Okay. Ooh, look what flies off the engine. There's a piston inside the engine. That's kind of cool. What's the piston made of? I don't know. But let's get 2 pistons together and smash them into each other at like the speed of light, and we'll see what goes flying off, and then we'll figure out what's inside the piston. So that's fundamentally how the physics department would approach this idea of what's the universe made of. They said, let's just smash things together and see what happens. Cool, okay? Now, the problem is that I can't take something like this, golf ball and try and throw it at this piece of aluminum foil, okay? Because if I want to make an atom-on-atom collision, the golf ball is a little bit too big. Because remember, I'm trying to hit a single one of those 95,000 atoms that are stacked up side by side by side. So obviously, whatever I'm going to throw at it has to be really, 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 really small, because I can't throw anything big at it. So Ernest Rutherford, and he's one of my favorite scientists of all time. He was actually from New Zealand. but he was doing work in Cambridge in England. And he was this big guy, had this great handlebar mustache, and a great personality, kind of a bigger-than-life personality. And so what Rutherford did what was known as the gold foil experiment. So what he did is that he had a box, literally it was just a box. And within the box, there was a source of radioactive material called thorium, okay? And thorium had a unique property that thorium would randomly go through radioactive decay. We'll talk more about that later. And so what that means is that the nucleus of the thorium was unstable. And it would randomly decay into something more stable. It's kind of, so imagine like you have like a tower of Jell-O, which is unstable, okay? And it doesn't take much of a wiggle, and the tower falls off, and then it breaks apart, okay? So that's what was happening. So the thorium was undergoing this radioactive decay. Now, what it was doing is it was shooting out these particles, and they didn't even know what the particles were. Okay, so these particles, they called them alpha particles. And the Greek, here's a Greek simple letter in Greek alphabet. This is the lowercase symbol alpha. Okay, it looks like a fish. Okay, because they didn't know what the particles were. They knew they were emitting particles. They just didn't know what they were. Now, here's the first thing I want you to get out of your minds. When we talk about these alpha particles, you cannot see them, okay? So everybody has this vision, like this, there was like this stream of golf balls being sent out from the thorium, okay? And they could actually see them. No, okay? You are sending out a subatomic particle, okay? So don't look like, oh, they can just see them. No, you can't see them, okay? Imagine trying to see an individual aluminum atom in this. Now, you can't see it. So, but they were clever. So what happens is that when these alpha particles, and they didn't know what they were, when they would hit a phosphorescent screen, it would make like a small flash of light. So what they did is they had this, so imagine that my room is dark, okay? And I've got this phosphorescent material up here on the wall. And I'd have that thorium sitting where the camera is. And there was a small opening in the box so that the particles could only go out in one direction. So I'd imagine that I've got that thorium source sitting where the camera is. The room is completely dark, okay? Little mood music, the room is completely dark. And this is a phosphorescent screen. So every time one of those alpha particles would be emitted from that box, what you would see is a flash of light, okay, on the screen. So that's how you knew it was going. So listen to me. You could not see the particles going. What you would know is that you would have a box there, and you would have a small opening. And then what you would begin to see is that you would see flashes of light up here on the screen. And every time there was a flash of light, they said, oh, whatever this particle is hitting here, and that's how they knew that something was happening. So listen to me. You could not see it, okay? All you can tell, there was a box there, an opening, and you would see flashes of light up here. Got that visual. The room is dark. Now, Rutherford being the physicist, he goes, huh, let's put something in between. So what he did is that he actually used gold foil. Okay? Gold foil has a very, very unique property because you can work it till it's basically one layer thick. So what he did is that instead of aluminum foil, he used gold foil. So he put the gold foil in between the camera and the screen. It was much bigger, okay? And he had graduate assistants that were literally sitting in this darkened room, so it would be like all of you sitting in the room. And we've got this phosphorescent material all the way around the room. And you all would sit there, and this is well before the days of computers or anything like that. Now, so they had pieces, they had a notebook, and they would make a mark wherever they saw the flash of light, okay? So Emma would keep track of the flashes of light here. Luke would keep track of the flashes of light over there, okay? You know, Peyton might keep track of the flashes that are happening over there. So everybody would watch a particular section, and they would make check marks that shows, hey, where are these flashes of light taking place, all right? So, got this gold foil, these particles are coming through. Now, the first thing that Rutherford had to figure out was, were these particles charged? So what he did is he used the same technique that J.J. Thomson did. So Rutherford put these big, massive plates on either side. And one was positively charged and one was negatively charged. So when these particles went flying through, they did the opposite of what the electrons did. So when these particles went through this electric field, here's the positive charge, here's the negative charge. And what happens is that these particles went the opposite direction of the electrons. These particles got repelled by the positive and attracted to the negative. Because, oh, cool, these things are positively charged. So what he knew about these alpha particles, he didn't know the mass, didn't know anything about them really, but he knew that they were positively charged. Okay, so imagine this. Here's the stream of particles coming out. You're seeing these flashes of light showing up on the screen. Okay, cool. He put the plates on them. He figured out that these are positively charged particles. Cool. So then he puts this sheet of gold foil in between. So these particles are coming through. It looks solid, okay? It looks like you could not see through this thing. So he put this thing up here. And he didn't really know what to expect. But here's the odd thing, is that even though there was a sheet of gold foil here, almost all of those particles still showed up like it wasn't even there. Like these alpha particles went straight through it. Now, every once in a while, what you would see is that you might see like a flash of light over here, okay? You might see a flash of light over there. And rarely what you would see like a flash of light over by the door. Like these particles got through the gold foil and they got deflected very, very much, like boom, okay? That was extremely rare. Now, literally what happened about 1 in a million times, we would see a flash of light in the back of the room, okay? Literally, it was 1 in a million. So what that means is that 1 in a million times, that particle would be emitted from that source. It would hit this, and then it would bounce straight back. It was 1 in a million. The vast majority of the time it went straight through. So that would be like me taking this golf ball, and I'm going to throw it at the counter, okay, at the cabinets. I throw it like this, boom. Now, I do that 1,000,000 times. 999,900 times, that golf ball actually goes through the cabinet. Like it doesn't bounce back. So if I threw this at the cabinet, and it didn't bounce back and it went straight through, what would you conclude about the cabinet? Solid or mostly empty space? Mostly empty space. Literally, that was the reaction. It was like, whoa, this is bad. This literally like completely shook the scientific community. Because what they figured out is that even though this appears solid, on an atomic level, it's mostly empty space. Okay? Like literally, these particles would go boom, and they would just pass straight through. You'd get a little bit of deflection every once in a while, but for the vast majority of the time, it was empty space. Now, here's kind of the analogy. You all know that on this thickness of this aluminum foil, if you were to stack those up, those aluminum ions or atoms, that's about 95,000 of them across this thickness right here. So what can you conclude about these atoms? Big or small?
Small.
Really, 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 really small. Okay? Now, here's what that got even weirder. Okay, atoms are small. We get it. Atoms are small. But this is what's completely shocked the scientific world. Not only are those atoms really, really small, within that smallness, there's a single dot. that contains 99% of the mass. This is 99% empty space. Then you're going, oh, Mr. Burkamp, don't be silly, okay? Look at it, okay? It feels solid, right? Okay? Can't really tear it, can't see through it. There's no way it's empty space. But that's what they concluded. I was like, you know, and this is why what happens on an atomic level is so counterintuitive to a macroscopic world, okay? Because the atomic world is so weird, okay? So they sit and they go, okay, well, this is bad, okay? This is very bad. Because, like, how do you explain that all of that positive charge was concentrated in one small space? So this is kind of the analogy. Imagine that I have a golf ball, okay? And I'm going to put that down like on the 50-yard line of the football field, okay? So this would be like the nucleus. The alpha particle would be like this tiny, like a BB, okay? Have you ever seen like a BB, all right? So imagine I've got this golf ball at the 50-yard line, sitting there like this. I'm going to be in the end zone, and I'm going to try and shoot a BB randomly at that golf ball, okay? Really can't aim it. I'm just going to randomly shoot BBs out there. Most of the time, what are the BBs going to do?
Yes.
Pass right through, okay? Now, sometimes the BB might hit and glance off. That's what would happen when you would see these flashes of light on either side. It would hit and it would bounce off. And literally, if I shot those BBs out there, what would happen is that 1 in a million times when I shot that BB would come in and it would hit this dead on, and then it would bounce straight back. Okay? So that happened 1 in a million times. It would hit and it would bounce back. Most of the time, those BBs just go straight through. So here's what they concluded about Rutherford's experiment. Number one, there was a nucleus. Okay? Now, he knew, and this is key thing, he knew that the alpha particles were positively charged. Okay? This is a key thing. He knew the alpha particles were positively charged. So, what that means is because it would hit and it would bounce back, that means whatever it hit also had a positive charge, or otherwise it wouldn't repel each other. So imagine that you have two particles that are both positively charged. Here comes this BB, it's positively charged. It's going to hit this nucleus, positively charged. They're going to hit, boom, they're going to bounce back. Okay? So like what we did with the balloons, they would hit and they're going to bounce back. So the nucleus is positively charged, and it contains 99% of the mass, but basically only about 0.1% of the volume. Okay? This is a huge problem. The scientific community goes like, there's no way this is right. And here's the reason why. Because the plum pudding model was cool. Okay, we have Legos. It was a very visual type idea. We got Legos. The plum pudding model, it's evenly distributed, it's stable, hey, life is good. Rutherford comes along and says, whoa, 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 whoa. You shoot positive charged particles at this thing, they go straight through. 1 in a million, it hits and it bounces back. Now everybody's like going, well, we're screwed now. How do we explain this? So what they had to come up with was a new force, and it was called the strong nuclear force. Not the most clever of names. So what they had to be able to explain was that how the nucleus was stable. Now, I can say this, I want to give this analogy, because I grew up with 3 older sisters, okay? So the protons are like girls that don't like each other. Somebody said something about Snapchat, whatever social media that you like, okay? And maybe this was back in 7th grade, they wore the same dress to the prom, or to the dance, I don't know. But these 6 girls hate each other, okay? They're completely repulsed by each other. If they saw each other like walking down the hall, they would literally go down other hallways to avoid each other. They hate each other that much. Okay, so this is what protons want to do, because they all have the same charge. These protons want nothing to do with each other. So then they're going like, well, how do we explain this? How do we explain these girls that don't like each other are all crammed into a small space, and then they're very stable? So here's the best analogy that I can give you. Imagine that you take those same 6 girls and you put them inside a Volkswagen Bug. Okay, so they're confined into a very, 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 very small space. Like, you got to cram these things in there. Okay, but once you get them there, oh my God, they are the best of friends. They're taking selfies, Snapchats, you know, okay, they're posting on all this. Oh, look at my besties. Okay, it's incredible. Okay, they're like doing each other's hair. It's wow. Like, oh my God, miss you so much. Wow. Okay. Tightest bond you could ever have. However, you get those same 6 girls outside of that Volkswagen Bug again, they hate each other again. Okay, they're going to be completely repulsed by each other. So that's basically what happens inside a nucleus. So the protons don't like each other. They want to go flying apart. So what physicists came up with, it was a rather clever name, they called it the strong nuclear force. So the strong nuclear force is stronger than the repulsive force that makes it go away. But it only acts over the shortest distance. It only acts over an incredibly short distance. So you've got to get these protons incredibly close before the strong nuclear force takes over, and then they're held together. Now, later on they figured out there were neutrons. Why do you think it was tough to figure out that there were neutrons? Why do you think the neutrons were the last subatomic particle to be discovered? What charge do neutrons have? None, okay? They're lumpy, they're big. They don't interact with any. So protons and electrons interact with electric fields. Neutrons don't, okay? Because they don't have a charge. So that's why the neutrons were last to be discovered, because of the fact that they don't interact with anything. Okay, stop that camera for a second. I know you've been sitting for a while. Okay, so here's the first 2 bits of terminology that you've got to get straight. We've got to talk about 2 different things. The atomic number and the mass number. Mass number. Okay? So the atomic number is the number of protons. And the mass number is the total number of protons and neutrons. Sometimes you'll see protons and neutrons lumped together in something called nucleons. That isn't used very often, but sometimes you'll see it referred to that. So the atomic number, and this is where this gets a little bit weird. The atomic number is actually shown by the letter Z, and the mass number is shown by the letter A. Now, you would think the atomic number would be shown represented by the letter A, because that would make sense. Oh, atomic number, that starts with A. Let's make that A. And then the mass number, oh, let's that be M. Don't know why, nobody really knows, but that isn't the hand that we're dealt. So the atomic number is actually shown by the letter Z, and the mass number is shown by the letter A. Okay? Just accept it, don't fight it, go, that's stupid. Don't argue. Okay? You're not going to win. If we haven't changed it in 100 years, we're not going to change it, because Mr. Burkham's first block honors Chem 1 class goes, well, that's stupid. We need to change that. Yes?
You're teaching compliance.
Huh?
You're teaching compliance.
No, I'm teaching the fact that you're not going to change the scientific community. So it's just like electrons and protons. That's a whole other discussion about how electricity moves. We screwed it up from the beginning because Ben Franklin guessed wrong whether what particles were positive and negative. He had a 50-50 shot and he guessed wrong. Okay, and we still haven't gone back and changed that in terms of like how electricity actually moves. Ben Franklin thought it was positively charged particles that move. He literally he had a 50-50 shot. He could have chose positively charged particles or negatively charged particles. He chose positively charged particles. Turns out the electrons move. We haven't gone back and changed that either. Okay, and it drives all my physics students crazy. They go, Why don't we change it? Because we don't, okay? It's just the hand that we're dealt. This is how it works. Okay, so when you look at the atomic number, okay? Now listen to me, what I'm going to tell you very, very carefully. If you want to figure out the type of atom that it is, and we've talked about this, the only thing that determines the type of atom is the number of protons. It is not the number of electrons. It is not the number of neutrons. Okay? It is solely the number of protons. So if something has, for example, on this sheet, if something has 6 protons, no matter what you do with the electrons, no matter what you do with the neutrons, anything with 6 protons is going to be carbon. Okay? It might have 6 neutrons. It might have 7 neutrons. It might have 8 neutrons. Okay? It might have 6 electrons. It might have 8 electrons. It might have 10 electrons. Okay? Those don't matter. It is only, listen to me very, very carefully, it is only the number of protons that determines the type of atom. Now, that's a good thing though, because the nucleus is so incredibly stable, that's why I don't have to worry about this table turning into something different. Okay? It's not going to turn into a squirrel because the number of protons that make up all these atoms is incredibly stable and it's not going to change. Okay? And you don't have to worry about it either. You don't have to worry about your DNA like exploding in the middle of the night going, whoa, my DNA just came apart. Okay? No. Okay? Weird. It's not going to happen. Okay? Things are stable. But they're stable because we're not going to change the number of protons. Okay. So what you're going to do is that you're going to get in your normal lab groups, and y'all are going to have this. And you're also going to have a tub, and you're going to have different colors of marbles. You're going to have green, blue, and clear. Okay, so these are your 3 types. So what you first need to decide what's going to happen is that up here, you need to decide, and there's no right or wrong answers, you need to decide which are the protons. If you want the protons to be blue, make the protons blue. Neutrons, if you want those to be clear, make them clear. If you want them to be green, I don't care. So the first thing that you all need to decide as a group is that what do you want the particles to be? Which colors do you want them to be? Now, let me explain how this is going to work. So, this is like a blown up view of the nucleus. Okay, now, we really couldn't build this to scale. So, there's a couple of things that I don't like about this. It shows you the structure, but it is nowhere to scale. If we were to build this to actual scale of an atom, these, we would have to go out to the football field, and where we would put the nucleus would be on the 50-yard line, and it would be about the size of this apple, okay? So that would be the nucleus, right? Is the camera going?
Yeah.
Okay, good. Just talking about this. Oh my God, I hope that's good. So this would be the nucleus. To make it where the electrons are, that would actually, we would have to go out to where the stands are around it. Okay? That's how much empty space there actually is. So this is not in any way, shape, or form to scale. Okay? Not even close. But it's a good visual model. Now, here's the other thing that's technically wrong with this. What you'll notice is that these are like layers. So like the inside layer, this is where you're going to put the electrons. So this inside layer is only capable of holding like 2 electrons. And that part's right. But this makes it look like the electrons are stable and they're like in one place. In reality, these electrons are moving close to the speed of light, going around here, creating an electron cloud. So we put them here mainly because of the fact that it allows us to get a visual. In reality, this is not what's happening. Okay? These electrons are moving close to the speed of light. If the nucleus was here, we would have to, literally, if we were here, we'd have to put the electrons basically down where like the gymnasium is. That's how far they would be away. And we'd have to have them moving close to the speed of light in a circle. Really not practical in terms of something we can do. Okay, it's like, yeah, we need everybody out of the gymnasium because I'm going to have kids running around carrying electrons, and they're going to be running at close to the speed of light. Okay, really can't do that. It would be cool, don't get me wrong, but probably not going to happen. So what you're going to do is that you're going to have a Tupperware like this with different color markers. Okay, then you're going to have a stack of playing cards. Okay. So what you're going to do is you're going to pick out, and you're going to start with this, and you're going to start off, everybody's going to start the same. You're going to have an atomic number of 6, so you're going to have 6 protons, and you're going to have 6 neutrons. So figure out how you want to count this out here in the nucleus, which is in reality right here, okay? But we're going to build it out here because we don't have room to stack them in there. So this is the nucleus. This is what this kind of little gap here is showing. Oh, this is the nucleus and this is where it would be, but we don't have room to build it in there because we can't build it to scale. But imagine this is the nucleus. So you're going to come in here and you're going to put in a total of 12 particles. 6 protons, 6 neutrons. Dink, 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 okay? You're going to have those. Then you're also going to have then 6 electrons. Now, here's the rule with the electrons. And this will make sense later on, because Mother Nature was a lazy prima donna. You always start and you fill the inner levels first, and then you work your way out, okay? So stamp in here, this is going to say 1s, okay? So the 1 tells you the energy level that's closest to the nucleus. So you always fill the energy levels closest to the nucleus because those are the most stable. So you're going to put 2 electrons here. Then you're going to start to fill the second energy level. Then you're going to start to fill the third energy level. And then you're eventually going to end up here in the fourth energy level if you get to that many. So 1, 2, 3, 4. And again, this isn't realistically valid because it shows them as being static. They're not. But this is the best that we can do in terms of making this work. So what's going to happen is that you're going to build the first one, and then you're going to draw out a card. So let's say I pull out this card. And then I'm going to say add 2 protons and 2 neutrons. So I'm going to come here to the nucleus, and I'm going to add 2 protons and 2 neutrons. So then I'm on this one. So this is an example. So this next line that said, so Bob, okay, it's funny because that's my dad's name. So Bob drew out a card and it said add a neutron. So notice what happens, that it's still an atomic number of 6. We're still going to have 6 protons, but now we're going to have 7 neutrons and a mass number of 13. Now, for now, don't worry about this isotope symbol, okay? We'll get to that later, okay? Don't worry about this. The only thing I want you to fill in for now is the atomic number, number of protons, number of neutrons, number of electrons, and mass number. So, and the element name, because it's carbon, that's 6. So what I want is this, basically the first columns up through mass number. Do not worry about the isotope symbol. We'll get to that later. Okay? So this isn't going to take very long. So basically you've got this up through these sections on the back and make that happen. So what you need to come up and grab a board, grab a Tupperware, and what you're going to do is you're going to fill these in, and then you've got these questions, summaries on the back. Okay, what does change the number of protons do? What does the number of neutrons change? What does change the number of electrons change about the atom? So, here's the deal. Atoms, y'all can figure this out. If the number of protons equals the number of electrons, what do you think the overall charge of the atom is? Positive or negative? Or neutral? Neutral. Okay? Now, if you have more electrons and protons, what charge do you think the atom has?
Negative.
Negative. If there's more protons than electrons, it's probably going to be positively charged. Okay? So the electrons are like these little mosquitoes that are flying around that are like the chihuahuas of the world, okay? So, and remember, the protons and neutrons are like these big lumpy St. Bernards. So here's the domain of the St. Bernards and the German Shepherds, okay? They're showing up, they're going, okay? And then this is the realm of the Chihuahuas. So the Chihuahua realm, the St. Bernards, and the German Shepherds. Okay, so go grab a tray, grab a piece, grab Tupperware, and make it happen. Okay, so this, yeah. Okay, you?
Yeah.
Well, okay, I think it might be the sign of the apocalypse. Okay, I'm serious. Anyway, so let me kind of explain what the shortcut method is. So this is just a way of conveying a lot of information in a very, very, very concise, small way. So what this is known as there's different versions of this. One known as the isotopic symbol. Sometimes we'll see it called the complete atomic symbol. So the reason that it's called like the complete atomic symbol is that you're going to convey 3 bits of information. Which element it is, the atomic number, the mass number, and then if it needs it, then the charge. Okay? So it's always the same way. So this is also kind of like why you put the mass number on top and the atomic number down below, because it's like the alphabet. You put A up here and then you put Z down here. Okay? That's kind of the way. The other way that then it allows you to subtract to find the number of neutrons in a particular nucleus. So here's how this is going to play out. So if you look at those first 2, you've got carbon 12 and then you have carbon 13. Hello, here, come grab this. Okay? Now, up here with the charge, as long as the number of electrons equals the number of protons, then there is nothing that you write up here. Okay, so the only time you put anything up here, erase, is when there's an imbalance between the number of electrons and protons. So if there's nothing up there, it's just assumed that it's neutral. Okay? Now, let's say, so somebody give me a situation where your number of protons don't equal the number of electrons. Ellen, look at your chart. Find one example where the number of protons don't equal the number of electrons.
The what?
Look on that row. Give me an example where the number of protons doesn't equal the number of electrons.
I don't even know what you're talking about.
Okay.
What do you mean?
Look across one of your horizontal rows.
7 and 6.
Okay. Which one's which?
What do you mean? Oh, protons is 7, electrons is 6.
Okay, 7 protons, 6 electrons, and how many neutrons?
6.
Okay, so you got 6 neutrons. So what we need to do is convey this information on an atomic symbol. So because we have 7 protons, which element has 7 protons?
Nitrogen.
Nitrogen. So I'm going to put an N for nitrogen. Okay? Now, down here is the atomic number. That's the number of protons, which in this case is going to be 7. Okay? So this number here tells me which element it is. Okay? So if I see a 7 here, I'm going to put nitrogen. If this is a 6, I'm going to put carbon. If this is an 8, I'm going to put oxygen. Okay? So anything that has 7 is going to be nitrogen, no matter what. No matter what happens with the neutrons, electrons, doesn't matter. Listen, it is the number of protons that determines the element. Not the neutrons, not the electrons. Only the number of protons. Okay? Now, up here, I'm going to put mass number, which is the total number of protons and electrons. So in this case, I'm going to take 7 and 6, and I'm going to put 13. Now, for the charge, because I have 6 electrons and 1 and 7 protons, do I have an extra positive charge or an extra negative charge? Extra positive, extra negative. Keaton. Yeah, so I'm going to come up here and I'm going to put a 1 plus. Now, if there were only 5 electrons, I'd put 2 plus, because then I'd have 2 more positive charges than I have negative charges. If I had 8 electrons and I had an extra negative charge, then I'd come in here and I'd put 1 minus. So here's the anomaly, is that a negative number up there actually means that you have added an electron. Okay, so negative numbers means that you've added electrons. Positive numbers actually means that you've lost electrons relative to the number of protons. So here's what I want you to do for tomorrow. I want you to finish this column here where you fill out that isotope symbol for every element that you have. Now, on the back side, now you can answer these questions. What does changing the number of electrons change about the atom? That alters the charge on the atom. If you have extra electrons, it's negatively charged. If you have extra protons, it's positively charged. So what I want done for tomorrow is fill out these isotope symbols, and we'll take that and run with that tomorrow. Yep.
The 7 is the protons
Yes.
up there on the isotope.
Yes. Yes. If there was a 6, I'd put a carbon. If there was an 8, I'd put an oxygen. Yep. Yeah, so this is the atomic number here,
Okay.
and that's the mass number up there. Your mass number has to be greater than or equal to your atomic number. In your situations, your mass number is always going to be bigger than your atomic number. Only with hydrogen are the two equal at 1. And here's how you can check that you got this right. If you take your atomic number and subtract that from the mass number, that should equal the number of neutrons. So that's how you can check that you got this right. When you get done with this symbol, if I take 7 minus 13, I'm going to get 6. That should be the number of neutrons that I have in that nucleus. So that's the other reason that we stack them like this, because then we can subtract to figure out the number of neutrons. Okay? Got it? Good? Grand? Okay. So finish that column, answer the 3 questions on the back.